Okay, so by now we should know what a radical is. That was introduced to you last week. What's, for all intents and purposes, what's another word that you could use for a radical? Who said it? Jonathan? Yeah, square root. Okay, at least for now, that's the only type of radical we're going to deal with. So you say tomato, I say square root. No biggie. Okay. Yesterday we were introduced to adding and subtracting. What were the rules for adding and subtracting radicals? Same index.
And same radical.
And the same radicand. Good. This morning somebody tried to state a claim that said that, well, hey, but you said that the radicals have to be in simplest form as well. Well, technically they don't. As long as the first two rules are adhered to, nothing says that in order to add or subtract, the radicals have to be in simplest form. It says they have to be the same. It says if they're not the same, simplifying is something you can try to do to possibly make them the same. If the radicals are not the same, you can add or subtract. So this is important because now when we're introduced to multiplying, the rules kind of change. But you look at the first one, you're like, hey, look, the indexes still have to be the same. And yes, that is correct. You cannot multiply a square root with a cube root. You can't multiply a cube root with a fourth root. But unlike with adding and subtracting, if the indexes are not the same, eventually there will be something that we can do to make them the same. You won't be able to do the actual multiplication until they become the same. But it can be modified. We can modify the indexes to make them the same. We cannot do that with adding and subtracting. For right now, we don't have to worry too much about that because we're only going to be dealing with one index leading up to the quiz on Friday. And I want to say again, well, actually not. Because before the test, we might see some other ones. But it shouldn't be more than at the most maybe a cube root. What type of index does a cube root have? 3. Okay. The other difference is when it came time to actually add or subtract, what part of the radical was added or subtracted?
The radical?
Mm-hmm. Radical stay the same. The coefficient, good, yes, the outside, as TJ said. So now with multiplying, that's going to change. Now we're going to multiply inside with inside, which if you want to use fancy words, we can call that the radicand. The radicand. But then we're also going to multiply the outside with the outside. Those are those coefficients. The rules for division, which we do tomorrow, are kind of the same, but division throws something else in there known as rationalizing a denominator. That's probably why you're going to like division the least, because it has the most steps. Well, how do we multiply? Well, really, it's just a process of 2 steps. How did we add or subtract? Well, we only really needed to look for like radicals, and then you said it. Add the coefficients. Well, here there's 2 steps. It's multiply and simplify. And typically, I would teach them in this order. I think universally, this is what requires the least amount of steps, is if you do it in this order. But there's a different dynamic that we're going to have to deal with before the quiz on Friday. Anybody want to take a guess? If you do it this way, and indeed you multiply first, what normally happens when you multiply numbers, at least whole numbers? What tends to happen to those numbers? They get what? They get bigger, right? So when it comes time to now simplify a radical, which in many cases involves doing a tree, you're going to be doing a tree with a much bigger number. So I'm going to show you how to do it both ways. Okay. The drawback of simplifying first is, in some cases, if you simplify and then multiply, you might have to go back and simplify again at the end. You might have to simplify twice. So I've always taught it in this order, but yeah, this could mean that you're more reliant on a calculator. So without further ado, I apologize for the size of this. It's just taking too long to just write over it with a thicker pen. So I'll do this. I'll turn off the lights right in front of the board. Hopefully that helps a little bit. That says 2 square root of 6 times 5 root of 27. In future units, I'm going to use a different software, which should remedy this.
Is it 27? Yeah.
I'll write that in thicker. If we were to multiply first, what were the rules for multiplying? Index is the same, but okay, both of these are square roots. So you know what the index is, find out the both square roots. So then when it comes time to multiply, where do we multiply? Outside, outside, inside, inside. On the outside, what's 5 times 2? On the inside, oh man, I need my calculator. Yeah, it is 162. If you can do that without a calculator, great. Okay? If you can't do that without a calculator, well, here, I'll show you what else you can do. Once we get to this step, even if you can't do it, number one, like if you actually can't get to this step because you don't know what 6 times 27 is, or if you think, oh well, hey, 162 is too big of a number, you should at least be able to tell me what I would be doing next. Once I get to here, what do I want to do next? Simplify what? The radical, yeah. Simplify the radical, the number on the inside. And what is that going to involve? To do a factor tree. Well, what your other option is that instead of doing one big tree with 162, you can do multiple trees before you multiply. So like if I were to do a factor tree with a 6, which that's what's here. That's just 2 and 3. There's no pairs there, but if I'm looking for prime numbers, I know that I have a 2 and a 3. If I were to do a tree with a 27, I would get, well, I don't want a 9 because 9 is not prime. I would get 3 3s. So in total, what prime numbers did I end up with? 1, 2, and 4 3s. Take a wild guess when I do a tree with 162. Take a wild guess what I'm going to get. 1, 2, and 4 3s. So if you feel comfortable with your multiplying skills and your factor trees, and you want to get the 162 first, and then do the tree, that's fine. If you want to deal with the factor trees when the numbers are smaller, you can do that as well. The point is that you still have to multiply the coefficients. 5 times 2 is still 10, but now underneath that radical, whether you deal with them when they are separate, or whether you deal with it when it just becomes one big one, we have to end up with a square root that has a 10 on the outside, 1, 2, and 4 3s on the inside. Because this is a square root, the index is 2. In order to get out, we have to pair them up. What do we have pairs of? 3. So we have 2 pairs of 3s. So who's going to join the party on the outside? 2 3s. I already have a 10 there. Madison Catogio. What is 10 times 3? 30, and then times another 3? Good. And what's going to stay on the inside? Yeah. Fantastic. So on the outside, she did 3 times 3 times 10. And she ended up with 90. And I apologize for the thinness of the writing on here. I'll try using a different software for the next unit, but at least for the last couple lessons we have in this unit, if you download it from eClass, that would be another thing you could do so you can see it better. I can see the resemblance. Oh. Yes, ma'am. I did do that. That's what. When I use these trees, that's by simplifying and then multiplying. Yeah. I gave you 2 for 1. In that dark blue, that's where you see simplifying first, and then I did the multiplying afterwards. But like the whole thing is, once we get to here, well, now that's it. We've already done both steps. We multiplied because 5 times 2 is 10. And then we simplified because whether you did it as a 162 or whether you treated them separately, underneath the radical, you have to end up with a 2 and 4 3's. Okay. All right, here's another one. No! Right when I was starting to understand this guy brings back the letters. Math should not have letters involved. It should only be numbers. And then really small numbers at that.
It is a number.
You are right, yes, a variable is a number. It's an unknown number. Yeah. Okay, so just some things to be aware of. We still are multiplying. And you could multiply first. If you're not scared of mental math, and you choose to multiply first. On the outside, these are both square roots. On the outside, we have 2 times 10, which is 20. On the inside, we have 12 times 6, which is 72. How many x's do we have? Yeah, we did that since polynomials. If you have the same x's, you add the exponents. 3 plus 3 is 6, right? So if that doesn't scare you, you should end up with 20 square root of 72 x to the 6th. And then now we would look to simplify. We would do a tree with a 72, and we figure out how many x's can come out. Mackenzie, if you want to simplify first, you would do a tree like here with a 6, which that's just a 2 and a 3. Can't bring anything out, but at least I know that's a 2 and a 3. I would do a tree with a 12, which is 2 2's and a 3. So I know eventually, like whether I did it using a 72 or whether I did it before, inside the square root, once they become combined, inside that square root, I should have 3 2's and 2 3's. And how many x's should I have? 6. 3 and 3 is 6 x's. If you just want a little peek, I'll show you the whole thing when we finish, but look, 3 2's, 2 3's. Once we put all the prime factors underneath one radical, underneath one square root, the square root says I need pairs to get out. So Madison Kelly, what do I have pairs of? One pair of 2's. One pair of 3's, so I'm bringing out a 2 and a 3, good. Fantastic, and 3 pairs of x's, yep. What's going to stay on the inside?
The 2.
The 2. Question?
Wait, so since there's 3 x's, is it going to be 1.5?
Every circle, that's why I use the circles. For every circle, it comes out once. So I circled a pair of 2's. That's going to come out once. What's 20 times 2?
That's 40.
40, yeah. Then we bring out a 3. What's 40 times 3? 120. You bring out, there's 3 circles of x's. So we end up with 120, x to the third on the outside, square root of 2 on the inside. But wait, mister, we have a quiz, and I remember the last time you were big on showing work. What steps do I have to show? Okay. Well, there's got to be at least 2 steps. There's got to be simplifying. There's got to be multiplying, right? So simplifying. What would simplifying be? That would be in the form of a tree. If you want to do 2 separate trees, that's fine. If you want to do 1 big tree after you multiply, that's fine. Okay. Then I would if you choose to do the multiplying first, okay, then you would show me the multiplying, then a tree, then you could come straight to the answer. That's fine. The 2 in the middle are not necessarily necessary. If you choose to simplify first, then you probably want to show me at least this step, and then you can come straight here. So really, like in no case, like this step right there is purely optional. Too many arrows, Alan? You look like you're confused by the arrows. No. Any other questions, Keon? We're good? Hey, I'm telling you, there's a resemblance with what's on your paper. It almost looks like a face. No! Stop it! No! Me no like it. What's different?
Parentheses.
Yeah, not only the parentheses, but why? Why do we need to use the parentheses?
Because
we're multiplying on the last 2. How many terms are in the parentheses? 2. So yeah, so people saying that there is a need to distribute, yes, you'd be correct. When you distribute, you are multiplying. So just follow the rules for multiplication, just do it more than once. Now, see, like even if you chose to try to simplify first, it wouldn't get you very far because 5, why can't 5 be simplified? It's prime. And even though 15 is neither perfect nor prime, you can't bring anything out. There's no pairs. So really here you have no choice. You have to multiply first. There is no simplification that can be done. Now, yeah, maybe you want to do that tree already with the 15, so you can turn it into 3 times 5, and then you'll realize that when you multiply it, like with the 5 that's on the outside and the 5 that's on the inside, you'll be able to bring it out. But I don't know, maybe that might be more confusing. I would just tell you, okay, inside with inside, outside with outside. What's outside the 5? A 1. What's outside the 15? 1 times 1 is 1. What's 5 times 15?
75.
75. So I have a square root of 75. Then Luna, there's still a 1 outside the 5. This negative 3 is also on the outside. It's not underneath a square root. So what's 1 times negative 3? Shush, Luna. It is. And because the negative 3 doesn't have a radical, then it would just basically merge with the square root. What is square root of 5 times negative 3? It's negative 3 square root of 5. Math makes your stomach hurt? Makes my stomach hurt. Okay, well, now I've removed the parentheses, which is something that's critical to simplifying. What am I still being asked to do? What are we still being asked to do? Subtract. So we jumped into our time machine and we pumped it up to 88 miles per hour. And we went back in time to yesterday where we had to subtract. In order to subtract, we need same index, same radicand. We have same index, we don't have same radicand, but what have we not attempted to do yet?
Tree.
To simplify, yeah. Maybe it helps, maybe it doesn't. That's why I like this example, because yesterday, a small sample, we don't have 3 hours to just do example after example after example. That tree magically always worked. And it made the radicands the same. Look at what happens here. If I do a tree with a 75, there are those 2 5s I was looking at. So I'm able to bring out 2 5s, but what's staying on the inside? The 3. Are the radicands the same now?
Yes, they are.
No, they're not. So I still can't subtract. Now, we're always expected to leave any expression in simplest form, so you wouldn't leave it this way. Even though you can't subtract, you wouldn't leave it this way. If you do, you're going to lose at least half credit, at least. You're going to leave it, but you're going to leave it this way as it is on the bottom. That is simplest form. Yes, on the bottom, this is simplest radical form. But wait, Mr. Romero, how about if I were, oh my God. I just blew your mind there. Oh man. Whatever. But Mr. Romero, what if I were to put 3 square root of 5 minus 5 square root of 3? I would have had it backwards. That would be fine, right? No, but the sign would be off. The order doesn't matter. It's not about the order, but if I mean, there really is no reason for you to do so. But if you were to change the order, that 3 square root of 5 would have to still be negative. The 5 square root of 3, that's the positive. There's no reason to do that, but I mean, if you want to be picky, that's right. Writing, like flipping just these two and leaving the minus in the middle like that, no, that would be wrong. Any questions there? Hang in there, Tanaya. Almost there. 2 left. Jonathan, I think I see a lawnmower outside. No, just kidding. I don't see it. I thought I did. Okay, how about this one here? What's different? I see parentheses, but we saw parentheses last time. What's different here? Both parentheses have 2 terms. There's 2 binomials. So how am I going to multiply?
You're going to use each one.
If only it had a name and I could try to say it as much as possible. Jonathan? Foil, good. I'm going to foil. That's what you're going to say? Now you're going to want to listen to this. Because this is going to save you some time. Let's learn the rule. If I foil, the first thing I'm multiplying is square root of 6 times square root of 6. Gabby, what would you say? What's square root of 6 times square root of 6? Square root of what? Okay, you could say that. What would be a better thing to say?
Radical 36.
She said square root of 36. And it isn't that she's wrong. Julia? Yeah, it's 6. Because what is a square root of 36?
6.
So what conclusion can we gather from this, right?
You're multiplying the same.
What do you call it anytime you multiply a number times itself? What's another way of describing it?
A square.
Squaring. 5 times 5 is saying 5 squared. Well, geez, a square? Square root, man, those sound similar. I wonder what they do to each other.
Boom.
Yeah, they cancel each other. So anytime you multiply a square root times itself, the radical explodes and you're left with just what's on the inside. You can put square root of 36, but you can't leave it because the square root of 36 is 6. Okay? How about square root of 6 times square root of 3?
18.
Square root of 18 sounds good. How about negative 2 square root of 3 times square root of 6?
-2.
Okay, on the front you're going to keep the negative 2. Then? Square root of 18 sounds good. And now the last one, let's really focus on this one. Negative 2 square root of 3 times square root of 3.
That's -2. Oh, no. That's -2. Yeah, negative.
No, definitely not 6.
-6.
No, see, TJ I believe he was starting to say negative 2 square root of 9, but then he caught himself because what is the square root of 9? So if you were listening before, when you multiply any square root times itself, you just get whatever number was inside. Take a second, look at that, breathe it in. If you're confused about something, let me know. You're going to sound back in. If you're not sure how I got one of those, let me know.
Wait, so the -2 and 3. Did it twice.
Well, yes, even though the 3's started on the inside, because you multiplied it times each other, the radical blew up. Now that 3's on the outside, so yes, not only can I multiply it, I will multiply it with a -2. Because now I'm just following PEMDAS. I'm following order of operations. Multiplication comes before adding and subtracting. And what is -2 times 3? -6. And then when it does come time to add and I go looking for like radicals, now this won't always happen, but it happened here. What is a positive 6 minus 6?
0.
0. All the 6's cancel. Yes, ma'am. Radical 6 times radical 3 gave me positive radical 18. They're both on the inside. 6 times 3 is 18. But that's good. Like, those are the type of questions I like. The ones I always kind of shake my head at is when people say, like, oh, I don't get it. And I say, okay, what don't you get? And I say, oh, I don't get anything. That's somebody that doesn't really want to focus. But see, that's a good question. How did I get square root of 18? If you don't know how I got, like, 2 times 3, like, let me know, like, before we go forward. Now, this worked out beautifully because I said this morning, somebody took the position that, hey, radicals cannot be added. You really want to say something, don't you? Go, say it. I can tell you want to. Go. What? You just look like you're like looking at me, waiting for me to turn around so you can say something. Is square root of 18 in simplest form? No. Does that mean that I can't combine it? No, if I wanted to, I could, because they're the same. They both have a square root of 18. If you want to simplify first and then combine them, go right ahead. And actually, and that can be simplified. You could pull out a 3 from there. I think on this one, I just chose to combine them first. I kept square root of 18 the same. What is 1 minus 2? Negative 1. Which is just negative and then square root of 18. But I can't leave it like that because I'm not in simplest radical form. Madison Picard, what's the last step? Last step? Do a factor tree. I can bring out a 3 on the inside. We still have a 2. Don't forget that the negative was already outside. That's going to stay outside. Right now that negative is joined by a 3. So we have negative 3 square root of 2. Last one. Even if you're a super duper radical person, I would pay attention here. I would say that the kids that know what they're doing make as many mistakes on these as the ones that don't. Because it's just natural instinct that C number outside parentheses must distribute. Don't write this. 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 But everybody wants to do that, and they want to distribute the exponent.
Write it out twice.
Mm-hmm.
Yes.
Exponents are not distributable over addition. In terms of being separated by addition or subtraction for that matter, you cannot distribute an exponent, you can only distribute multiplication or division. So what we use here is we get creative, as Deshaun said, he's a very creative fellow. And he said, well, geez, hey, if squaring a number is the same as multiplying it times itself, I might not know what to do with an exponent and a binomial, but I know how to multiply binomials. So what's being squared here? Earthing, as the cool kids say. So
Everything.
just multiply everything times itself. Multiply that one entire parenthesis times itself.
Even do like 9 and 7.
No.
9 and this square 14. 49.
No. I would be wrong. Yes.
What if it was Q instead of?
What if the 3 was outside of the parentheses?
Write it out 3 times.
Yeah.
You're asking me a what if? Like what happens if this 3 was out here?
No.
Or the 3 up there? Then you'd have to multiply it 3 times. But you won't get any of those. Now, there is something known as a binomial expansion. But I don't even think we get to that in Georgia. I don't think we get to that in Algebra 1. Maybe on something like this where it's only a square, maybe we'll get around to showing you eventually. But for right now, this is what I want you to handle it. Because now we at least know what to do. What do I do now?
Foil.
Foil. All right. So look, we have a few minutes. Why don't you guys foil this on your own? I'll give you like maybe 90-second head start, and then I'll come in behind you with the steps. Madison, you finished? Okay, first step after you just FOIL. Should look like this. If you haven't finished it, don't look up yet. Restrain your impulses. If you did attempt to do it on your own and you didn't get what I have on the board, holla. And let me know what you didn't get, and then we can figure out. Yes, sir.
I didn't get 9 parentheses 11.
Okay. So let's see how I got 9 times 11. That was on the first part of the distribution, for the first part of the FOIL where I did what's 3 times 3? 9. What's square root of 11 times square root of 11?
121.
Well, no, see, you could say square root of 121, you could, which would give you 11, but we don't need to go that route because we learned today twice that any square root times itself is just the number on the inside. So even if you were to write down square root of 121, you wouldn't want to leave it there. Anything else that's up there that is confusing to you? Yes. Well, which one? There's 2 of them. Okay. The second one came from 3 square root of 11 times square root of 7. On the outside is a 3 and a 1. So 3 times 1 is 3. 11 times 7 is square root of 77. The second one came the same way. On the outside 3 times 1. On the inside 7 times 11. Yep. You want to finish it off finally with the last one, the 7? You know how I got 7? Square root of 7 times square root of 7 is just 7. Before we get it, could you combine like terms now? You actually could, but if you're going to follow order of operations by letter of the law, we're supposed to multiply first. 9 times 11 is?
99.
99. 9 times. Okay? Then we get to here, and now we want to combine. I could definitely combine the 99 with the 7. What's 99 plus 7?
106.
106, we're definitely going to do 106. But then what do we do with the radicals? Well, they match. So if you want to combine them now, you can. You should try to simplify because 77 is neither prime nor perfect. But if you try to do a tree with 77, you just get 7 and 11. There's no there's no pairs. So that's actually going to stay just like that. It's going to stay as is. 77 in a tree is just 7 times 11. There are no pairs. 7 and 11 are both prime numbers. You can't do anything with it. There's no pairs. I'll leave you with one last thought. I tried to explain this today, and I still had somebody come up and ask me a question afterwards. Hold on. But wait, mister. Can I just add 106 plus 6? I know how to do that. Why can't I add those? One term has a square root, the other one doesn't. For lack of a better word, they're not like. It's the same thing as if a 6 had an x and the 106 didn't. It behaves the same way. They cannot be added. If it was multiplying, they could be multiplied. They can't be added. You leave it as is. Okay? We'll leave it there. You can sign out.